when we hit the 20 mark, we'll get ourselves started.
Okay.
Welcome everybody. We're gonna get started in just a couple of minutes.
Okay, I pasted the link in the chat window.
Great. Yeah, this one's actually one of my favorite talks because it's very interesting and apropos to. I mean, it's obviously very Stata specific in the commands, but the subject
Right.
matter is very applicable to a lot of
Yeah.
a lot of different applications. So
This is one of my favorites as well.
are you training your next generation of someone who's gonna do this after you?
We can talk about that when we're not recording.
Understood.
Well, yeah.
Okay. Because you are a walking encyclopedia in yourself when it comes to things related to Stata.
Well, it's partly repetition. I mean, this talk that I'm doing today, I bet I've done this talk, I'm not exaggerating, at least 50 or 60 times, at
Well, I'm sure.
least.
I mean, you've
And
done
so when
it
you do it
five
over and
times,
over and over.
probably 5 or 6 times. I probably heard it 5 or 6 times in my tenure. So,
Well, and I have 38 of these things. And so
mhm.
there are a lot of these that just due to sheer repetition, like the Bayes stuff, it's, you know, I couldn't get it out of my head if I wanted to.
All right, well, we have hit the 20 mark.
Okay.
Welcome everyone. Thank you so much for joining us today for our Stata series. My name is Dr. Joni Ricks Odie, and I direct 2 units on campus. So I direct the UCI Center for Statistical Consulting, which is in the statistics department. And then I also direct the Institute for Clinical and Translational Sciences BIRD unit, and BIRD stands for Biostatistics, Epidemiology, and Research Design unit. Both of those are units of epidemiologists and statisticians, and our mandate here on campus and our mission is to support you all. And that would be sometimes with one-off drop-in consultations around study design or formulating statistical analysis plan or data analysis. Additionally, we can be on grants. And one of the things that we do is we want to equip you all to the extent you are interested and being able to do some of your own analysis, or if nothing else, even if you're working with a statistician, have a good handle on some of the methodology out there that sometimes can be intimidating, and an understanding of how to conduct some of these analyses and think through the theory and methodology. And so we are joined by Dr. Chuck Huber. He works for Stata. I have known him for, oh boy, now we're going on 2 decades.
Too long. Longer than we want to admit.
Longer than we want to admit. And he is a fantastic resource and repository of all things Stata. He's been doing this for a very long time, and has honed and created the subject matter, like the presentation you're going to see today was created by him. It'll be presented by him. Please don't be intimidated. Chuck is wonderful. He is happy to field questions while we are going through this. My staff and I will also monitor the chat. You'll see on camera right now is Margaret Errol. She is my business manager, so she and I will be monitoring the chat. And then additionally, if they wouldn't mind, a couple of my staff members are on here. So Dr. Marissa Erickson, I'll tell her to wave if she can, and come off, put her video on for a second. I have Kate Kirby, who is with the center. Arnie is one of our GSRs. And again, we're here to support you all. And so if there are any questions, we will help try to field them. And we want this to be as beneficial as possible for you. So again, I'm going to turn this over to Chuck and Margaret. Let's go ahead and start recording.
Yeah.
Okay. Oh, are we recording?
We are.
I think we are already recording. Okay. All right. Well, thanks, Joni, and thanks everyone for being here today. Let me share my slides really quickly, and I'm going to shut off my video because that's not really necessary. Well, I thought I turned it off. There it goes. Just a little housekeeping item. I've had COVID for the last week and I'm fine. I took Paxlovid or whatever, but I may start hacking and coughing. This is the first thing I've done. First time I've crawled out of bed in over a week. And so if I start coughing, I apologize in advance. I'll get it under control and be back. And today's a good warm up for tomorrow because tomorrow, shameless plug, Stata Corp is doing our 2025 Epidemiology and Biostatistics Conference online. So I don't know if you can still register for that, but we've had about 3,000 people already register. So that's tomorrow. And I'm hosting, so I've got to get this cough under control. Okay, so today we're going to be talking about causal inference for complex observational data, of course, using Stata. And I posted why is it not changing the slides here? There we go. I posted a link in the chat window, this link here, this tiny URL where you can download all of the slides and data sets and do files. There's also a do file in there that creates the simulated data set that we'll be using. So if you want to simulate these kinds of data, turns out that's not a trivial thing to do. So if you want to do that, the do file that I use to create the simulated data set is in this download as well. Along the way, if you have any questions, please just unmute your microphones and ask along the way. I'd rather just tackle things along the way, and it gives me a chance to grab a sip of water while you're asking your questions. So don't hesitate to just unmute your mics and ask anytime. Okay, so here's what we're going to do. We're going to start off with a description of the data set, and then I want to talk about three things that often come up with observational data. First being unobserved confounding and endogeneity. The second thing is non-random treatment assignment, and then third is going to be data that are missing not at random, or MNAR, which can lead to something called selection bias. And then we'll wrap up by talking about treatment effects at the end. So, excuse me, there we go. So we're going to start with a research question, which leads us to our fictional data set. So Fictional State University, FSU, has developed a new study skills program with the goal of improving their students' grade point averages. So the treatment that we're interested in is the study skills program, yes or no, and the outcome of interest is the students' grade point averages when they finish. So this is the little data set that we're going to be using. It is completely simulated fake data, so don't believe any of the results you see here. It's strictly for instructional purposes. But this data set includes the following variables. There's a variable called ID, which is the student identification number. There's a variable called GPA, which is the student's final college grade point average. We collect their final GPA when they graduate from college. And then there's a variable called HSGPA, which is the student's high school GPA that we collected when they were applying to college. And then there's a variable called program, and it's an indicator for whether or not the students took the study skills program. So it's yes or no. Graduate is also an indicator variable for whether or not the student graduated from college. Income is the parent's income measured in hundreds of thousands of dollars to keep the numbers very small. Computers don't like really big or really small numbers, so that's income. It's continuous. HS Comp is a measure of high school competitiveness. I wrote this talk, I don't know how many years ago now, about 7 or 8 years ago. And at the time, there was no official measure of high school competitiveness. I've since heard that the College Board has developed an official measure of high school competitiveness. This is not that measure. This is just something I made up for our purposes. And it's a continuous variable. Roommate is an indicator for whether or not the student's roommate is also a student. And then scholarship is an indicator for whether the student had a needs-based scholarship or not. And we'll come back and talk about those variables as we need them along the way. Okay. So the first thing I do with any new data set is I like to summarize it. And I really am not interested in the mean or standard deviation column. The main thing I'm looking at first is the OBS column. Because I want to see if I have to deal with any missing data. So if I look down the OBS column, all of the variables have 1,000 observations, except for GPA. College GPA only has 792 observations. So what does that mean? That's kind of a non-trivial amount of missing data. It's a little over 20%. So I may have to think about multiple imputation or full information maximum likelihood or something because it's not 3 or 4% missing. That's over 20%. So I'm probably going to have to address that at some point. So I like to know that right out of the gate when I get a new data set. The other thing I like to do is scan down the min and the max column just to look for any weird values. And you really should do a deeper data cleaning before you start using a new data set, but these are simulated data. But I usually look at the min and max to see things like GPA. GPA should be bounded between 0 and 4. And so the minimum is above 0 for both GPA and HSGPA, and the max is below 4. So anyway, I don't see any weird values in the min or the max column for these variables, but just something else I like to look at. So the main issue I'm noticing is this GPA only has 792 observations. So the next thing I'm going to do is start tabulating some of the data. So here I'm tabulating the variable graduate. So of the 1,000 students in my data set, 792 graduated, 208 did not graduate. Well, wait a minute, that 792 looks familiar. So if I scroll back here, that matches the number of students that I have GPAs for. Well, that kind of makes sense because I only get the students' final college GPA when they graduate. So if they didn't graduate, I don't ever observe their college GPA. So that explains partially why I'm missing GPA for 208 students. So again, I'm just getting to know the data for right now, but that may sort of explain why I'm missing some data for GPA. I like to do some descriptive graphs of things. So this is a histogram of final college GPA, and I've overlaid a histogram on top of this. Excuse me, I've overlaid a kernel density plot on top of this. And this is your first clue that these are fake data because no data ever looks that neatly hump shaped ever. But anyway, so everything kind of ranges between 0 and 4. It's unimodal. I don't have any sort of bimodal. I don't have two humps in the middle of this. I don't have wild skewness or anything like that. So I'm just kind of getting to know the data. This looks like it'll be a nice dependent variable for my data set. Another thing I like to do, some people like to do correlation matrices with the continuous variables they may include in their models. I prefer to use scatter plot matrices because correlation only measures the degree of linear relationship between variables, and you can often notice more interesting patterns in scatter plots. So this is a scatter plot of matrix of final college GPA, high school GPA, and parents' income measured in hundreds of thousands of dollars again. So, what am I looking for here? Well, the first thing that jumps out at me is there appears to be a very strong linear relationship between final college GPA and high school GPA. No surprise there. If you did well in high school, you probably do well in college. And so it's not a surprise. It's just a feature of the data that we should probably be aware of. The next thing I've kind of noticed is high school GPA and parents' income seems to have a fairly strong linear relationship as well. There's kind of a slight upward trend to that scatter plot for our parents' income and high school GPA. There's a similar pattern for parents' income and final college GPA in the top right corner. Doesn't look quite as strong as parents' income and high school GPA, but there does seem to be a similar kind of an upward pattern to the scatter plot there. So again, just getting to know the data, looking at the features and relationships here. I know a lot of people don't like pie charts, but I only have two categories here. And so this is a pie chart for the study skills program participation. And you might assume, I probably would have, that it would be roughly 50-50 in terms of study skills participation. 50% no, 50% yes. But that's not what we have here. Only 30% of the students in our data set actually took the study skills program. 70% did not. So that variable is very unbalanced. It's not even 50-50. So again, not a problem or anything. It's just a feature of the data that we should probably be aware of. Now, some more descriptive graphs. Here on the horizontal axis, I have final college grade point average. So this is my primary dependent variable. And then I've done two box plots for program participation. So the bottom box plot is for students who did take our study skills program. The top box is for students who did not. Now, those lines in the middle of the boxes are the medians, not the means, but nonetheless, it's a measure of central tendency, and it seems to show that students who took our study skills program had a lower median final college GPA than students who did not take our study skills program. This is kind of disturbing because the point of the study skills program was to improve the college GPAs, not make them lower. So this is a really awkward result, and we're going to have to look into that. In fact, if we fit just a basic, simple linear regression model for just college GPA and program participation, so I've typed regress GPA, and then the I dot in front of program is Stata's factor variable notation that tells us that program is a categorical variable or indicator variable. If we look at the coefficient on program participation, it's negative, which suggests that students who participated in our program had lower final college GPAs. Well, this is really awkward because that's the opposite result that we were looking for. So now let's go back and look at high school GPA. So the horizontal axis now is high school GPA. And again, the two boxes, the bottom box is students who did participate in our program, and the top box is those who did not. And again, we see a similar pattern where students who did take our study skills program had lower incoming high school GPAs. So let's think about the temporal order of these events here. We collected high school GPA on the way in before the students took the study skills program. So there's no way that our study skills program could have caused the high school GPAs to be lower. So the students then take the study skills program, and then they later on we collect their final college GPA. So the order is high school GPA, program participation, and then college GPA. There's no way that our study skills program could have caused high school GPAs to be lower because we collected it first. So there's this pattern that we're going to need to deal with along the way in our data analysis, and we're going to come back to it, but it's just a descriptive feature of our data set that we should be aware of going before we start building complex models. Okay. And in fact, if we just build a little regression model, the same one we did before, and adjust for high school GPA, notice that the coefficient for program participation actually flips direction. So when we adjust for incoming high school GPA, the program participation coefficient flips to positive and suggests that the study skills program actually improved high school GPA, or at least is associated with improvement in college GPA. So something interesting is going on here in our data set. More descriptive graphs. So the horizontal axis now is percent graduating. And the two boxes, the bottom box again is yes, students who did take our study skills participated in our study skills program. The top box is students who did not. And again, we see this pattern where students who did take our study skills program had a lower graduation probability than the students who did not. It seems like the students who took our program participation had poorer outcomes in general than the students who did not. So again, just getting to know these things. This is graduation status by high school GPA. So again, students who graduated tended to have a higher incoming high school GPA than students who did not graduate. So all of these, again, they're just features of our data that we're getting to know before we start building a complex model. What we really want to answer, the question we really want to answer is, what was the effect of the study skills program on the students' college GPAs? So, in order to answer this question, we need to think about the things we've seen in our data set, and we also need to think about some potential issues we may have with observational data, because this is, in fact, an observational data set. This was not an experiment. So the first thing we want to think about is unobserved confounding and endogeneity. So this may be a new concept for a lot of us if we've not taken a econometrics course before. So let's zoom out for a moment and talk about linear regression in the abstract, or any kind of regression for that matter. So let's talk about just a generic outcome variable y. So we would say that y is equal to all of the possible factors that could influence y. And we're going to divide up those factors into two groups, the observed factors and the unobserved factors. So the observed factors are those variables that we have in our data set, things that we actually measure, and they often appear in our data set. The unobserved factors are all collected into the statistical garbage can that is the error terms or the residuals. And if you're like me, a lot of us were not really who were not trained in economics or econometrics. We don't really think about those unobserved factors. We just sort of dump them all into the error terms and don't really give them a lot of thought. So, before we come back to that, let's talk about endogeneity, or define the term endogeneity. So, endogeneity, according to Jeff Wooldridge's Intro Econometrics book, endogeneity is an explanatory variable in a multiple regression model that's correlated with the error term. So let's say that I have two covariates in the model, x and z, and for some reason, z is correlated with the error term. So that's the definition of endogeneity. So the question obviously comes up, well, how would that happen? How would you end up with a covariate that's correlated with an error term? Well, one way, not the only way, but a way that this can occur is something called omitted variable bias. So let's say we have two covariates in our model, x and z are correlated. This happens all the time. It's called multicollinearity. So if X and Z are correlated and they're part of the observed part of the model, if for whatever reason Z is not included in the model, maybe we didn't measure it, maybe it's just difficult to measure, but for whatever reason Z is not in our data set, Z doesn't just disappear into thin air. Z moves from being part of the observed part of the model to being part of the unobserved part of the model. So Z moves into the error term. So now we have error star in this middle equation here, and error star actually includes Z. It's an unobserved variable that gets bundled into the error term. Well, if Z is correlated with X, if we know that, and Z is part of the error term, then X and the error term, error star, have to be correlated by definition because Z is now part of error star. Okay. So that is a way that you can end up with this issue of endogeneity. Now, why do we care about this? Well, as the term implies, omitted variable bias. This can actually bias the estimates of beta 0 and beta 1 if we have this correlation between X and the error term. So we don't want to have biased coefficients, especially beta 1, because beta 1 could be the effect of our treatment, for example. So if beta 1 is biased, then we don't know the true effect of the treatment on the outcome. Okay, so that's omitted variable bias. If you're not familiar with the concept of omitted variable bias or endogeneity, often in the health sciences, particularly epidemiology, this is referred to as confounding. So this turns out to be confounding is actually a complicated term. In the Encyclopedia of Epidemiology, Sander Greenland wrote the entry, and he points out that there are at least 3 different uses of the term confounding in the world of epidemiology. And there's a really nice paper on the history of the use of this term. So anyway, we're going to have to just pick a term or pick a definition. So today we're going to be using Judea Pearl's definition of confounding. So we're going to say that X and Y are confounded when there's a third variable Z that influences both X and Y. So if Z is in the model and we believe that Z influences Y, well, of course, that's why it's in the model. If we also believe Z influences X, that means it's in some way associated with it. It's a confounder. Well, again, what happens if Z is this confounder and Z is not included in the model for whatever reason? Z then becomes an unobserved confounder. It's a confounder that moves into the unobserved part of the model, into the error term. Okay. So then again, we have this issue of correlation between X and the error term, which is again called endogeneity. So whatever you call it, endogeneity or unobserved confounding, the concept is the same and the consequences are also the same. We could have a biased parameter estimate for beta 1 or other parameters in the model, and we don't want that. Okay, so what does this have to do with our data set? So let's think about GPA in this context. So GPA is our outcome variable that we're interested in, final college GPA. So college GPA is equal to all of the possible factors that could influence GPA, and we're going to divide those into observed and unobserved factors. So the observed factors are things like high school GPA, SAT scores, parents' income, sex, things that we probably have in our data set or could measure easily. But let's think about the unobserved factors. What are some unobserved factors that might influence college GPA? Well, they could be things like ability, motivation. Sleep is kind of easy to measure these days with smartwatches and things like that. But maybe support, emotional support, financial support's easy to measure. But what about things like emotional support? Well, these are things that are often not measured, but we sort of stipulate they exist and they probably do have some impact on GPA. So let's think about something like ability, someone's ability. How exactly do you measure that? Let's assume that we believe that ability is a thing and ability influences your final college GPA, but ability could also influence something like your high school GPA. And if this is the case and we don't measure ability, ability could be an unobserved confounder that we need to think about. So again, if ability influences final GPA and ability influences high school GPA, that makes ability an unobserved confounder. So first off, how are we going to identify that this is an issue? Well, here's where the math starts getting a little funny, so just bear with me for a moment. Let's take this model at the top. GPA is equal to beta 0 plus beta 1 income plus beta 2 high school GPA, and we're going to assume ability is bundled up in that error term. What I'm going to do is I'm going to take high school GPA out of the primary model that we're interested in. And I'm going to build what I'm going to call an auxiliary model, where high school GPA, I'm going to pull it out of the model, the primary model, and create this auxiliary model where high school GPA is the dependent variable. And I'm going to fit that model using a covariate that has some important properties. I need a covariate, and I'll come back to what it is and why in a moment. I need a covariate that is associated with the outcome of the outcome high school GPA, but is not associated with the unobserved confounder ability. So in this case, I'm going to use the covariate high school GP, or excuse me, high school competitiveness. And so here's my argument. High school competitiveness probably influences a student's high school GPA. More competitive, probably lower GPAs. Less competitive, maybe higher GPAs. So I'm going to argue that high school competitiveness could influence high school GPA, but is not likely to be associated with ability, because ability is a measure of an individual, whereas high school competitiveness is a feature of the school, not the student itself. Okay, him or herself. So, so that's the variable that I'm going to use in this auxiliary model. And that variable has a special name in the econ world. It's called an instrumental variable. Don't worry about the terms, but the concept is what's important here. So I'm going to fit this auxiliary model, and the expected value of high school GPA is this green part of the model, the pi 0 plus pi 1 high school competitiveness. That green part of the auxiliary model is the expected value of high school GPA. What I'm then going to do is I'm going to substitute instead of putting high school GPA in the main model, I'm going to put the expected value of high school GPA in the original model. So that's the second model here in the middle of the slide. Now, both of these equations have ability bundled up in their error term, if ability truly is an unobserved confounder. Ability would appear in both of these error terms. And if that's the case, that means these error terms are correlated in some fashion. The correlation between those error terms is not zero, okay? So this technique, what I'm doing here is not a new thing. It's actually something called two-stage least squares. Econometricians use this technique all the time. Again, don't worry about the jargon. The main thing here is the concept. I'm going to fit this auxiliary equation and then substitute the expected value of high school GPA into the main equation. Now, another way of thinking about this is actually, let's skip over the latent variable part. Let's draw this as something called a structural equation model. So GPA structural equation models are often drawn with a path diagram like this. So anything that has corners, these rectangles, these are observed variables in the data set. So GPA, college GPA, that's the main thing I'm interested in. High school GPA is a predictor of college GPA. Now these arrows between the boxes show the influence of one variable on another. So I believe that parents' income influences college GPA. High school GPA has an arrow to college GPA here. So I think high school GPA influences college GPA. And HS Comp, I believe, influences high school GPA. So I've drawn this as a path diagram. Now, the circles here, notice the circles have epsilon 1 and epsilon 2. The circles are the residuals or the error terms. Okay. And actually, let me go forward here. The circles are the error terms, and notice that they say epsilon 1 and epsilon 2, but they both circles, both error terms contain ability inside of them. So if both of them contain ability, that means that there's covariance between these error terms. They both contain ability, and if that's the case, there's this covariance or correlation between them. So what we can do to find out if there is this problem of unobserved confounding, if there's something in common in these error terms, is measure the correlation between those error terms. Well, we've gone this far down the structural equation modeling road. Let's go ahead and fit this using a structural equation model in Stata. So I've drawn this in the structural equation modeling builder, and I can fit the model. And I see that the estimated correlation between those error terms is 0.88. Well, that's pretty high by anyone's definition. 0.88 is a pretty high positive correlation. So that suggests that there's something in common in these two error terms, which in plain language suggests that we do have some unobserved confounding going on in our model here. So we've identified the issue. We do have a problem with unobserved confounding. What are we going to do to fix it? Well, the good news is the same technique we use to identify it is the same technique that we use to fix it. By fixing the model in this way and accounting for or estimating the correlation in the model, allowing for those correlated error terms, that actually results in unbiased or consistent parameter estimates in the model. Okay. So the diagnosis is also the solution here. So that's how we would do this using a structural equation model. But what we're interested in today is a newer, it's not that new anymore. It's been in Stata for three releases now, is a family of regression commands called extended regression models, or ERMs for short. And one of those commands is called eregress for extended regression models. And there are some others, and we'll talk about those later. But this is eregress. Eregress is for continuous outcomes like college GPA. So our dependent variable here is GPA. And then the next thing in our what I'm going to call our primary model is parents' income, because we believe parents' income is related to college GPA. What I'm then going to do is add the endogenous option here. And in the endogenous option, I'm going to fit my auxiliary model where high school GPA is the dependent variable, and I'm going to include any covariates that I believe influence high school GPA. So here I've included high school competitiveness as well as parents' income in this auxiliary model. Now, one thing that's important to point out is that the dependent variable the dependent variable in the auxiliary model, HSGPA, is included, or the expectation of it is included in the primary model. Okay. So HSGPA is actually part of the primary model up here at the top. And I could have typed it if I wanted to, but you don't have to. All right, so I'm going to fit a primary model and an auxiliary model. So that means when I look at my output, I have two sets of coefficients. One set of coefficients is for the primary model where GPA is the dependent variable. And I have a second set of coefficients for that auxiliary model where HSGPA, high school GPA, is the dependent variable in the auxiliary model. And then at the bottom, I see the variance of the error terms for the GPA model and the variance of the error terms for the high school GPA model, the primary and auxiliary models. And I get an estimate of the correlation between those error terms at the very bottom of the output. So on the next slide, what I'm going to do is zoom in on this red box. It's the same information. I just want to zoom in to make it easier to read. So at the bottom here, notice we get a correlation between the error term for the HSGPA model and the error term for the GPA model. And that correlation is 0.75. It's a little different than the structural equation model because I included parents' income in both models. But still, 0.75 is a fairly high correlation. And again, this suggests that we do have correlation between those error terms. And so we probably need to use this kind of a model to take that into account. So we can't just use regular linear regression here. We're going to need to fit a model like this that accounts for or allows for correlation between those error terms. And again, the good news is by using this model, not only have we diagnosed the problem, we've also solved the problem because by allowing for that correlation, it removes the bias in those coefficients in the primary model. Okay. So what I've done here so far, I'm not going to talk about it yet, but I'm collecting the results using estimate store. Let me back up. After I fit each model, I'm typing estimate store, and then I can type estimates table and look at the output or the coefficients, parameter estimates for each of these models. So Univar is that first model that I fit that only included program participation. HSGPA, that column is those are the coefficients from the model, the Univar model that adjusted for high school GPA. And then this NDOGE model, this last column on the right, that's the model that we just fit. And again, we're not going to go over the results just yet, but I am collecting results along the way. So that is unobserved confounding and endogeneity. Any questions up to this point? So far, so good? Okay. Well, next up, let's talk about non-random treatment assignment. So in a perfect world, what we would do is as the students come in, we would flip a coin. And if the coin comes up heads, we would say, okay, you're assigned to the study skills program. Their friend comes in behind them. We flip the coin again. It lands heads. So they go to the study skills program. Next student comes in. We get tails. They go to the no study skills program. The point here is that we're randomly assigning the students either to the study skills program or no study skills program, which makes the interpretation of our results at the end very easy. Because if we've randomly assigned them to the two groups, that means we've randomly, hopefully randomly distributed any observed or unobserved confounders between the two groups evenly. So any difference that we see in final college GPA should be attributable only to the study skills program participation. Okay. And again, it makes our interpretation of our results very easy. But that's not actually what we have here. We didn't do random assignment. What we did was random choice. We are not random choice, self-selection. So we asked the student, "Hey, do you want to be in our study skills program?" They're like, "Yeah, why not? I'll do it." Their friend comes in and they agree to do the study skills program as well. The next student comes in and says, "Nah, I'm fine. I don't think I need to go." So the point here is that the students are self-selecting into the two groups. Well, this screws up our interpretation at the end of the study because the results, any differences we see in college GPA, could be due to the study skills program, but it could be due to other factors as well. And those factors may have influenced the choice to participate in the study skills program or not. So it muddies up our interpretation at the end of the study. So what are we going to do then? Well, one thing we could do is we could fit a model for the choice to participate in the study skills program or not. So, what we could do is fit a probit model. We could, in any other day, we might could fit a logit model, but not here. We're going to use a probit model, which is a kind of regression for for dealing with binary outcomes. Econometricians love probit regression. So we could fit a probit regression model for program participation. And of course, that's going to include some observed factors and some unobserved factors as well. So when we fit that model, the other thing is that eventually we're going to want to put program participation in our primary model, right? Because program participation is our treatment we're interested in, and we're interested in its effect on final college GPA. So if we're going to put program participation in our primary model, we need to think through unobserved confounding again. Well, we talked about ability before, and in this case, we need to think about, well, we've already stipulated that we believe ability exists and influences college GPA. But would ability likely influence program participation? Well, it could. And here's why. If someone of higher ability probably knows their higher ability, they probably had higher high school GPA. So they might think, well, I do okay in school, and so I probably don't need to take this study skills program. I'll be fine. Students of lower ability may have had lower incoming high school GPAs, and they may think, this is a good opportunity for me. I've kind of struggled in the past, so maybe I should take the study skills program. So in this case, ability may influence the choice to participate in the program or not. So we may again have this problem of unobserved confounding with program participation. So let's walk through this slide again. Now, don't take this slide literally. This is kind of a mathematical analogy to what we did before. It's not literally what we're doing, but it's the same idea. We're again going to fit an auxiliary model. This time the auxiliary model is going to be a probit model for program participation. And again, I need that special variable that is associated with the dependent variable program participation, but is not influenced or related to ability. So here's the argument I'm going to use for a needs-based scholarship. A needs-based scholarship should free up extra time from working or things like that so that the student has more time to participate in the study skills program. But a needs-based scholarship shouldn't be related to a student's ability or not, because it's a needs-based scholarship. It has nothing to do with their ability. So that meets our sort of definition of the special variable we need, this instrumental variable. And then we can substitute the expected value of that into the main equation. Again, this is sort of a mathematical analogy. So we're going to do this again, and again, we need to check for correlation between the error terms in these models. So I have program participation now influencing college GPA. Needs-based scholarship is influencing program participation. I'm going to again allow for correlation between the error terms between those two models, the primary model and the auxiliary model. And this is partly why I like drawing this as a structural equation model, because you can see the entire system of equations as a picture, and we can see that there's correlation between those error terms, or at least there could be. That's what we're going to check for. So let's take a look at our eregress command again. Excuse me. So again, we have our primary model, GPA. The command is eregress. The dependent variable is college GPA. I have income in that primary model. I still have my endogenous HSGPA auxiliary equation in here. But now I'm going to use the entreat option. Entreat is kind of similar to endogenous. It's going to fit another auxiliary model. But this time, because it's entreat, that tells Stata that program participation is a very special variable. That's our treatment variable that we're interested in. And that way, Stata later on in post-estimation commands and things like that, Stata will automatically know that program is the special treatment variable in our model. And it's going to fit this auxiliary model that includes both parents' income as well as needs-based, the indicator for needs-based scholarship. Don't worry about the no interact option for right now. That's just in there to keep things simple for now. So now we have a primary model and two auxiliary models. So when we fit this model, we now have three sets of coefficients, one for the GPA outcome model, one for the program outcome model, and one for the HSGPA model. Keep in mind those program coefficients are on a probit scale, so you can't interpret those the same as the linear regression coefficients. Okay, so again, like last time, I'm going to zoom in. On the next slide, I'm going to zoom in on this red box at the bottom so it's easier to see. So again, we get estimates of the variance of the error term for the GPA model and the HSGPA model. We don't see, you would think we would see, but we don't. We don't see the variance of the error terms for program participation, and that's because it's constrained to be 1. I don't know why we don't go ahead and put that in there and just tell you that it's constrained. We do that with structural equation models, but we're not here. But there is an imaginary third variance in here that just equals 1 for the error for the program participation. But what we do see in our output is the correlation between the error for the program participation and the errors for the college GPA. And that correlation in this model is 0.45. Well, is a correlation of 0.45 enough to worry about? Well, that's debatable. Maybe it is, maybe it isn't. For our purposes today, because this is what we're thinking about, we're going to leave it. We're going to say, yeah, if 0.45 is high enough, it's not 0. We could look at the p-value and say that it's not 0. We could look at the 95% confidence interval and say, well, it doesn't include 0. So we're going to roll with this, the idea that 0.45 is it's enough correlation to suggest that we do have a problem with unobserved confounding. And so we're going to leave this in the model. We're going to go ahead and leave this as a feature of our model. Okay. So if I add this to the table, now I have another column of coefficients in my collection of model coefficients here. Again, we're not going to look at the results just yet. I'm just showing you that we're keeping them, kind of hanging on to them. Okay, so any questions up to here? That's non-random treatment assignment.
Hey, Chuck, I don't know if I
Yes.
completely followed why we were doing a probit versus a logit, or maybe you'll talk about that later.
I kind of usually leave it out because it's a little bit nerdy, but the reason is because logistic regression models don't have an observation level error term. Let me back up to the structural equation model here.
That's right, it's
Pro,
phase. Okay.
yeah, logit models don't have an observation level error term, and so they don't have this error term to be that can be correlated with the GPA error term. Probit models, on the other hand, do. They do have an observation level error term. And so I actually thought originally that because this command was actually written by econometricians for econometricians, it really wasn't meant for the rest of us. I thought, oh, they're just using probit because econometricians like probit. But it turns out there's a mathematical reason. It's because logit doesn't have this observation level error term. So you can't correlate it with the other error terms.
I legitimately that missed. I forgot that, so I was like, that makes absolute sense.
Yeah, yeah, everyone does. And the other bit of trivia that everyone forgets is why is this variance not in here? And I ask that all the time, and only 2 people have ever known the answer to that question when I asked it. And it's because the variance of the error terms is constrained to be 1 in probit models. So, okay, any other questions about non-random treatment assignment? Okay, so let's move on to data that are missing not at random, MNAR, and the possibility of selection bias. So, first off, let's talk about data with no missingness. Let's assume that we had nice, clean, complete data here. Well, if we imagine that happening, we have a bunch of students who start off as freshmen and they take all their classes and they make it across the whole 4 years and they graduate. Yay! So that's good news for them. It's also good news for us because we have nice, complete data on GPA at the end of our study. So we don't have to worry about multiple imputation or FIML or any of this stuff. That would be great. But we know in our data set that's not the case because we have over 20% missing. We only observed 792 values of GPA out of 1,000 students. So we know we have missing data. So that then raises the question, how did that data become missing? Well, let's talk about some different ways that data can become missing. One of them is called missing completely at random, often called MCAR. So here the students go along, most of them graduate, but for some of them, something happens along the way that is completely random that stops them from graduating. So this student here at the bottom won the lottery. So yay, they won the lottery, and so they blew off school, bought an island, and they went away. And so that's good news for them, but it's bad news for us because now we don't observe their final college GPA. So that is kind of bad news for us. We're going to lose, our numbers are going to drop. We're going to lose a little bit of statistical power, but it shouldn't bias our results one way or the other. It shouldn't bias what we observe about college GPA because the reason that they're missing is so completely random that it just has nothing to do with their GPA. So we lose a little statistical power, but it shouldn't bias our results. So that's missing completely at random. There's another missingness mechanism, often called missing at random, which is unfortunate because it sounds like missing completely at random, but it's not. Missing at random, or MAR. Here, what happens is most of the students go along, take their classes, and they graduate. But for some of them, something happens along the way, like this student's mother lost her job and they couldn't afford to pay the tuition. And because this mother lost the job, we never observed the student's final college GPA. So again, we lose some statistical power, but it's bad news for the student. The good news for us is that, and just roll with this. This is kind of a stretch, but remember that parents' income is related to final college GPA, which means that we might be able to use that information, that relationship, to use multiple imputation to recover some of the information about final college GPA. Okay. So when data are missing at random, this is a good opportunity to use something called multiple imputation. And we're not going to go into the details today, but it's possible, there is a possible remedy to get some information back. So that's missing at random. Now, there's a third mechanism called missing not at random, or MNAR. And what happens here, let me start the video, is most of the students go along, take their classes, and graduate. But for some of these students, they drop out. For instance, this student drops out because they had said, this is just too hard. I give up. I'm already on academic probation. My GPA is in the toilet. They're going to kick me out anyway. I'm just going to go ahead and quit. Okay, so if we have a bunch of students like this in our data set, again, we don't observe their final college GPA, so we're going to lose some statistical power. But here's the bigger problem from our point of view. If those students are dropping out because their GPAs are low, that means not only are we losing statistical power, we're also chopping off the lower tail of the GPA distribution, right? Because if a lot of students drop out because their GPA is low, we're not going to observe those low GPAs in our final data set. And that's going to bias our GPA results upward. Okay, it's called selection bias. We're selecting students who happen to have higher GPAs because the students with lower GPAs just dropped out. Now that is a problem because not only are we going to lose power, but it could bias our results. Now, if you're like me, a lot of us were sort of taught well, now we just are there's no way out of this hole, but it turns out there is a way out of this hole that we're in. So again, if we think back about graduation, 792 of our students graduated. 208 of the students did not graduate. So we know that we have 208 students that are missing data. The question then becomes why? Or is it missing completely at random? Is it missing at random? Or is it missing not at random? Well, there's a way to check for data that are missing not at random. So what we're going to do is we're again going to fit a model for graduation status. We only observe their final college GPA if they graduate. So I'm going to fit a probit model again for whether or not the student graduates. And again, I have observed factors and unobserved factors in that model. So let's think about ability again. Ability could be an unobserved confounder for whether or not the student graduates in that graduation model. And what I need then is I need another one of these special variables that is associated with the outcome graduation, but is not associated with the student's ability. So in this model, this auxiliary model, I'm going to use the variable roommate. Roommate, again, is an indicator for whether or not the student's roommate is also a student. So here's the argument I'm going to make. If the student's roommate is also a student, their schedules are more in sync. They're going to be up late studying together, out the door early in the morning studying. They're going to kind of be in sync, which makes the student more likely to graduate. But if the student's roommate is their spouse and their mother-in-law and their three kids and their two dogs and cat, they've got a lot on their plate, which what might make them less likely to graduate, just because they're just overwhelmed and busy. But having a bunch of roommates, of family members, has nothing to do with your ability or not. So I'm going to argue that roommate will work here as an instrumental variable again. So what I'm going to do is I'm going to fit this auxiliary model, and I'm going to flip to the next slide here so I can show this as a structural equation model. And again, this is why I like showing this as a path diagram, because what I'm going to do here is I'm again going to allow correlation between the error terms of the primary model, where GPA is the dependent variable, and the error term for my auxiliary model, where graduation is the outcome variable. But notice that there's no arrow pointing from graduate back to GPA. Okay. Graduate does not appear in the primary model at all. All I'm going to do is fit this auxiliary model and allow for correlation between the error terms. That's it. Okay. And so we'll come back to that in a moment, but I want to really emphasize this. I'm going to allow for correlation between the error terms, but graduate does not influence GPA. It does not appear in the primary model in any way. So again, I have my primary model. Now I'm going to fit a third auxiliary model, but this time I'm going to use the select option. And again, it's a kind of endogeneity, and graduate is the dependent variable in this auxiliary model. And again, I'm going to include parents' income and roommate in this auxiliary model. Now, what makes this special and why I'm using the select option is, again, it allows for correlation of the error term between that auxiliary model and the primary model, but graduate will not be included back in the primary model. So that's why I have a different option here again. All three of these are dealing with endogeneity in some fashion, but select does not put graduate back in the primary model. So now when I look at my output, I have four sets of coefficients now. The primary model, where GPA is the dependent variable, and then the three auxiliary models where graduate, program, and HSGPA are each dependent variables in their own auxiliary models. And then at the bottom in the red box, I'm going to zoom in on that red box again on the next slide. Again, I don't see the variance of the error terms for the graduate model because, again, it's a probit model and the variance is constrained to be 1. But I do get a correlation between the error terms in that graduate model and the error terms in that GPA model. And if I look at that correlation, it's 0.76, very small p-value. Null value is not included in the 95% confidence interval. So 0.76 is a fairly large correlation, again suggesting that we do have a problem of endogeneity, or endogeneity or unobserved confounding with the model, with our auxiliary model. That suggests that we have data that are missing not at random. Now, again, the good news is by accounting for this in our model, it not only identifies the problem, it solves the problem. Now, if you're like me, you're probably wondering, how on earth does that work? And honestly, to this day, I don't have a good intuitive explanation as to why this works. So I'm going to have to commit the logical fallacy of an appeal to authority here. This technique that we're using is called Heckman selection. And it's a tried and true model that's been around since the 70s or earlier, actually. James Heckman won the Nobel Prize for this, I believe, in 1978 or 79. So not only has this been used for many, many years, but it also the person who invented it was awarded a Nobel Prize. So that's the only explanation I can offer as to why this technique works. All I do is fit an auxiliary model using this instrumental variable, allow the errors to be correlated, and that identifies and solves this problem. Okay. So how does this work? What am I doing? Actually, before we move on, any questions up to here? Any questions about data that are missing not at random?
I always have questions, but I'll let other people ask questions first.
Honestly, I would have never thought of this in a million years, and I have no intuition as to why. Or the others, I can kind of explain to myself intuitively why it works, but this,
Not quite.
it's sort of statistical magic that I don't really understand, but it does, evidently.
So what's I always think is kind of good and bad about statistics is we have a tendency to use the same terms for different things or maybe slightly related things that I think
Yes,
be confusing. And so
yeah,
in my mind, I was trying to analogize this to so in when you have missing at random, right?
yes,
Multiplication, there's the term of auxiliary variables, right? Which are
right, yes.
predict missingness are associated with the variable that is missing. Is do you have any intuition for like because you include that as like a variable in your imputation model, but it's a variable that then is not included in your actual like primary model. Is the
Right.
idea somewhat similar?
I've not really contemplated that at
Okay.
any for any length of time. It might be. I've taught multiple imputation off and on to various degrees of detail over the years. I just don't know. I get multiple imputation and I get the idea of why that works, but this is like sort of this strange voodoo magic to
It's the
me.
hand waving, the like the magic black box that you're like,
Yeah,
no,
I've
it
pondered
works, but
this.
we're not quite sure why it works.
I've pondered this, and I've asked smart people, and I have yet to hear. I can get mathematical explanations, but not a good intuition as to who would have thought of this and why to begin with. Anyway, we're almost out of time, so I need to wrap up here kind of quickly. The reason that I know that it works is because I created this is a simulated data set, so I know the true parameter values in this model. So at the bottom of the slide here are the true parameter values that I used to simulate the data. Now, this was not a simulation study. I created one simulated data set, not thousands and thousands and averaged over them. So this is one simulated data set. But the thing that I'm interested in, remember, is program participation. And that coefficient is zero point 0.3. The true parameter value is zero point 0.3. If I look across this blue box here, those are the coefficients for program participation. They're way off. The univariate model is in the wrong direction. HSGPA, that model was in the right direction, but still too small. In Dodge, we didn't even include program participation. It's not until we took non-random treatment assignment into account that we got a correct parameter estimate. So at that point, when we started taking that into account, we get a correct parameter estimate. And that carries over into even when we take the missing data into account. 0.2977 is real close to zero point 0.3. So once we take that into account, we get a correct parameter estimate. The other coefficients in the model, same thing. Let's look at high school GPA. Uh, Univar model wasn't included. The second column HSGPA that was off some. It's not until we take that into account in the starting in the NDodge model that we get parameter estimates that are around zero point 0.9 around the and once we take that into account in the rest of the models we get 0.9064 0.9022 0.8936 basically zero point 0.9. What's the other one? The income. Income is never really spot on, but by the time we get to the last model, if you look down that last end cell model, that's where we take all the features of the data into account. That's the only model that recovers pretty much correct parameter estimates, true correct parameter estimates for the true parameters that I use to simulate the data. So the point of this is that we need to take all of these features of our data into account when we model the data. Otherwise, we could have biased or inconsistent parameter estimates. And so that's what these eregress commands are about, is allowing us to correctly model or correctly specify a model for data that have these features. Okay. We're basically out of time, so I'm going to blow through this really, really quickly. There are post
Oh, I was gonna
estimation
say,
commands.
we actually advertise this as a like up to a 2 hour presentation. I mean, I don't know how many
Oh,
staff on,
okay.
but yeah, you shouldn't feel like we knew this was a longer one, so we let people know ahead of time that this was a longer presentation.
Ah, okay. So I don't need to rush through this.
Yes.
Okay, that's good to know. All right. So after we fit the model, Stata has this estimation, post estimation paradigm where we fit the model and estimate the parameters. And then we can do other things with that after we fit the model. So these include things like E-stat T effects, margins, margins plot, and predict. So E-stat T effects, what that does is it allows us to estimate the effect of the treatment on the outcome. Now, you might be thinking, well, I already saw that in the output. And that's true because we fit a very, very simple model. But we can have all kinds of interactions. You could have interactions between the treatment and other covariates in the model. What EStat T effects will do is tease that apart for you. If you do have other interactions or things like that in the model, it will average over all of those and give you the marginal treatment, the average treatment effect, accounting for all those interactions and things. There's another concept called average treatment effect among the treated, where we are only interested in the effect among the people who were observed to get the treatment. And so that's the ATET option on eStat T effects. Again, it looks really simple here because we fit such a simple model, but if we fit more complex, realistic models, this is a really useful tool so that we don't have to go through and do a bunch of algebra at the end. And it even gives us p-values and confidence intervals for that average treatment effect. So eStat T effects. Margins, which is probably my favorite command in all of Stata. Margins allows us, and that's essentially what eStat T effects is doing, is it's running margins in the background. But you can fit marginal predictions and then plot those marginal predictions, taking into account covariates in the model. So, for example, if I wanted to look at the treatment effect, the effect of program participation, accounting for incoming high school GPA, I could do that. Now, these lines are parallel because, again, I don't have any interactions between high school GPA and program participation. But I could have. I could have included that sort of interaction and then seen the results of that in my margins and margins plot. I'm not going to go through predict because it's kind of similar to margins, but there you can use the predict command. Now, I mentioned that this is a family of commands. We call them extended regression models, and they all begin with E. So I've shown you eRegress here for continuous outcomes, but there are other commands. There's eIntReg if I have interval outcomes, which you could argue that I should have used here because high school GPA is on or college GPA is on an interval between 0 and 4. So I could have used eIntReg in this example. If I have binary outcomes for my primary outcome, I could have used eProbit. If I have ordinal outcomes, I could use eOprobit. Of course, once we did this, the obvious question was, well, can we do this for panel data? Econometricians often work with panel data or clustered or repeated observations. And so you can do that as well. So if you need to fit these kinds of models for panel data, there's XT eRegress, XTE intreg, XTE probit, and XTE oprobit. So echoing the previous commands. Now, as I mentioned earlier, ERMs, extended regression models, can include all kinds of more sophisticated models. You can have polynomials of endogenous covariates. You can have interactions of endogenous covariates, interactions of endogenous with exogenous covariates. So you could fit way, way more sophisticated models than I've shown you here. This also works with survey weights, which just blows my mind. If a lot of times, almost always, survey data are observational data, right? There, you go out and do a very careful selection of data so that it's representative of some population, but it's pretty much always observational data. And we might be interested in causal inference with survey data, and you need to account for the survey weights. Well, all you have to do is survey set your data, SVY set, and then you just type SVY colon in front of those extended regression models, and you can take all of this stuff into account at the same time. So you've got survey weights, endogenous covariates, non-random treatment assignment, data that are missing not at random. All of those features can be accounted for in the same model. Okay. And again, you can use E-stat-T effects and those sorts of things after, even if you're using survey weights. Now, cautionary note, there's nothing in these commands that magically extracts causal relationships. And I put this in here, this cautionary note, because I sometimes I'll hear people say this, or I'll read it in discussion boards where people will say, well, I was using the regress command, but I wanted it to be causal. So I started using the sim command, or I started using the eregress command because I want it to be causal. It's not the command that makes it causal, and it's not the math underneath the software that makes it causal. The models simply allow you to correctly specify a model that accounts for the features in your data. That's what these models are there for. And if you correctly specify the model, and you have some reasonable underlying scientific rationale, you could make the argument that this is a causal relationship. But you still need that underlying scientific rationale. It's not just the math. It's not just the command that you're using that makes the relationship causal. So you still need to think through the science behind this. You can't just switch commands and magically extract causal relationships from observational data. Okay? So that's what I have for you today. We weren't running too far behind, especially since we had extra time. So, and again, we have plenty of time, so I'm happy to hang out and answer questions here. If you think of questions later on, shoot me an email at chuber@stata.com. I apologize in advance. I'm notoriously slow getting back to emails because I spend a lot of time traveling and doing this. And again, I pasted, and I'll do it again. You can download all the slides, data sets, and do files at tinyurl.com/2019 causal inference, and I will paste that back in the comments box again. Okay, so thanks for being here, um, and I'm happy to answer any questions.
Thank you, Chuck.
Thank you for setting this up, Margaret and Joni,
Oh, absolutely.
and thank you everybody for being here.
Just as a housekeeping thing, yes, we'll send out the recording to everyone, so you'll have access to that and can review the material and listen to Chuck's wonderful melodious voice. Again, whatever you would like. But yeah, please feel free to come off mute or turn your video on. Oh, it looks like Mandana has her hand raised. If you want to come off mute and ask your question, please.
Yes, so thank you so much for your wonderful presentation. I
Oh,
have a
thanks for being here.
question. Thank you. So I have a question. When in a real world we are modeling, we need a model. So for example, we are not sure that the only outcomes that affect graduations are parents' income and having roommates. There might be other variables that we don't know that affect graduation, not including those variables in our model. How this affect our estimation? Can we say that our estimations are still accurate, although we didn't include some of the variables that might affect graduation, or how is that?
Well, the honest answer is that we never really know. What that leads us back to the question of omitted variable bias, because if we can imagine other variables that probably should have been in the model that influence the outcome, then that means we probably are back in a situation where we have omitted variable bias of some sort. Now, the good news is I use the example ability throughout as our unobserved confounder. But the reality is I'm just giving it a name. There could be multiple unobserved confounders bundled up in those error terms. And there could be 3 or 4 or 5, and they could be different names. And so I never really know. So hopefully by using this sort of a modeling technique, that will sort of capture any sort of unobserved omitted variable bias issues. But I don't know how far you can push that. In the end of the day, you really want to specify a model as correctly as possible and include any observed confounders that you can. But you never really know. It's the things we don't know that we don't know. Those are the creepy things that show up in the unobserved, in the error terms. So,
Yes, that makes sense. Thank you.
sure.
Hey, Chuck.
Yes.
Nice to see
Hey,
you.
how are you?
I'm doing great, thanks. I was just looking at the Heckman command in the Stata documentation, And I
Yes.
haven't had a chance to read it, and I will read it, but I was wondering if you could just give a brief overview of how that relates to eRegress and what you talked about today.
It's the same thing.
Okay.
So, so it's kind of funny that these are not, it's a new command that came out, I believe, in Stata 15 or 16, but the stuff it's doing is really not new. In Stata, since for many, many releases, we've had, Heckman, which does Heckman selection. That's been in there for a long time. What's the other one? For the two-stage least squares command. I'm blanking on the term now, but that's been in there for ages. And then there are also the commands for dealing with MNAR. The Heckman's in there. What was the other thing? Oh, the T-effects commands for data that are not randomly assigned. So all three of those have been in Stata for a long time. What makes eRegress unique is you can handle all these features at the same time. So it's as though we've taken Heckman and bundled it, it's kind of squished them all together into one command. So you could do Heckman. If you only had issues with data that are missing not at random, you could use this, or you could use Heckman. But if you have issues with endogenous covariates and things like that, you would need to use eRegress. But essentially, it's the same thing, yeah.
But it sounds like eRegress is the most useful, most powerful one.
If you have
among them.
other issues as well, yeah. If you only have the missing not at random thing, then Heckman alone should be fine. It's the same
Okay.
idea. Yeah.
Okay, great. Thank you.
Good to see you. Yeah. Bye.
Anyone else have any questions that they would have for Chuck? Going once, going twice. Sold. All right.
Sold.
Well, thank you everyone for attending. We will again gather together next month. When's the date for the next one, Margaret? Do you know?
One moment.
It is March 12th.
Oh, there we go. What's the
thank you,
topic
Chuck.
for that one?
I happen to have it open because it has all the Zoom links in it. I'm sorry. What?
Oh, no, I said, what was the topic for that one?
I can get that too. Intro to causal mediation analysis.
Yes. So we're gonna have all kinds of fun with causal.
Yes.
So if that is your next month will be fun.
Yeah, that's going to get even more complicated. So we're going to take mediation into account too.
Wonderful. Okay, well then if we're all done and no one has any questions, we will give you some of your day back. Chuck.
Okay. All right.
Thank you, Chuck.
All right,
And to
thank you.
everyone
Thank you.
else, we'll be sending out the recordings and the slides soon.
Yay. Okay.
All right.
Everyone.
Thanks, Chuck.
Thanks, Margaret. Thanks, Joni.
Thank
Of
you.
course.
See ya.
Bye.
Bye.